Our discussions of turbulent combustion. I enjoyed our discussion yesterday, and I enjoyed all the questions that were asked, and again during the break, which I'll have to remember to take, I can try to answer more questions. The topic of our second day of discussion is listed here: kilohertz measurements of flame structures to assess models. Now this is, I'm going to summarize work done around the world, but also talk about what some of my own students are doing in this area. One of the things that the turbulent combustion community is trying to agree on, we don't always agree on much, but one of the things we're trying to agree on is canonical experiments. And Rob Barlow at Sandia, Nandas at Cambridge, DLR people in Germany, they're all leading this effort to decide on certain experiments and take measurements and do modeling and see if we can get them right, instead of everybody doing their own experiment. Now, I realize that many of you may need to set up your own experiment or do your own model of something that's not one of these canonical experiments, but if enough people can work on these experiments, we can hopefully get it right. And that would mean applying PLIF and kilohertz imaging diagnostics, and looking at things like vorticity and flame eddy interactions, and looking at other properties of the flame, such as the flame surface density, to assess models of combustion instabilities. Now, you know, Professor Kandel talks about instabilities in the morning session. It's a huge problem. You know, many rockets blow up, and they still don't have a good way to handle it. They put baffles, they put acoustic liners, and it's kind of like 1960 technology. And then when they say, let's build the rocket bigger, they don't have any model that will help them. You know, should I put bigger baffles? Should I put different acoustic liners? They sort of have to redesign a rocket engine every time. And a lot of that is true of the gas turbine engines too. That, if you scale them down or you scale them up, we don't have good models that can avoid engine growl and instabilities. So what are some of the canonical flames that people have identified? The turbulent jet flame, you can download this information off the internet. It's been studied, and we have huge amounts of data. The jet in a co-flow is very popular, especially if the co-flow is hot, such that you have auto-ignition. And this is the Cobra burner, the Sydney burner. A jet in a cross-flow is more practical. There are many devices. In fact, yesterday I showed you a GE fuel injector. The main fuel is injected as a jet in a cross-flow. And that's because if you have an air stream going at high speed perpendicular to a fuel stream, you're going to get very good mixing. The worst thing you can do to mix two fluids is to have a jet in a co-flow. You know, if the air is going this way and the fuel is going this way, the only mixing will be at the shear layer at the boundary. Unfortunately, you know, the Saturn V and the Space Shuttle main propulsion system, they had rocket engines in which they used co-flow injectors, because if you have to put 1,000 of these in on the faceplate of a rocket, you can't always have jets in cross-flow or complicated things. Sometimes you just have to have a jet in a co-flow because it's easy to build. And jet surrounded by swirling air, I talked about a little bit. There's been a lot of work on gaseous jets, but not nearly enough work on spray flames. And so we've had national meetings here. What do the engine people want, both auto and jet engine people? And they want sprays, because most of the things that you fly on or ride on, many of them have start with liquid fuels and with complex hydrocarbons. And so if you go to the Combustion Symposium in Seoul, we're going to see a whole lot of studies on methane. And in fact, my students are going to give some papers using methane, and it's time we move to other things. But we still haven't solved the problem with methane, and so it's hard to move on to other fuels. These are some of the experiments that I put on the slide. Robert Cheng at Lawrence Berkeley Lab put a small amount of swirl, and he was able to get a premix flame that was relatively flat, but then it sort of has edges on the side. And we've run a slot Bunsen flame, which is a rectangular fuel tube. Obviously, we'd like to have it as long as we could to make it two-dimensional, but that becomes dangerous and expensive. A V-flame is another premix flame that's a canonical experiment, and they've simulated this. This is a simulation as well as the one of the slot burner by Bell at Lawrence Berkeley Lab. The Sydney group, Professor Masri, have looked at a jet premix flame. And in Germany, they're running very large premix flames in gas turbine type geometries. And there's a huge database on all of these now, and still not enough, but a large enough database. And so when you say, who's using this? Well, these are the people on the left who are doing the experiments. There have been some DNS of some of these at Cambridge and at Sandia and at Lawrence Berkeley Lab. And then there's been LES done of almost everything, because LES is relatively easy to do. But it's hard to know which of these LES techniques is best, because they're all based on totally different assumptions. And then right here, Princeton, Professor Zhu, who introduced me yesterday, he's been doing a classic experiment where he preheats different fuels, and these are, I didn't write down what fuel these are, but these are higher hydrocarbons like butane, propane, and he's really moving into the field of real fuels, although this is gaseous fuel, and he's running Bunsen burners and looking at the structure. He's preheating the reactants, which is a little bit like a jet engine. So this is a motivation for the slides that are following. Some of you may have used some of these diagnostics, and maybe you've heard about them from Professor Lin. But me scattering used to be a major technique, and that's being replaced. But if you put oil drops in a premix flame, you see they disappear at the flame front. Rayleigh scattering allows you to measure the temperature field, and I'll say a few words about that. PIV is a fairly standard technique you can purchase off the shelf. OH-PLIF is very useful. It tells you where there's OH, but oftentimes that's only part of the story. Many people get confused at what OH really tells you. For example, just because you have OH doesn't mean you have chemical reaction, at least not the main heat release chemical reactions. And to think about that, suppose you had a Bunsen flame, just a conical Bunsen flame, premixed. Suppose it was nearly adiabatic. Then all of the gases that are downstream of the flame would have OH forever. OH would just stay there, because the water vapor would dissociate at high temperatures, and as long as it stayed hot, there'd be OH. So the OH doesn't tell you where the main chemical reactions occur. It just tells you where there's hot water vapor. CH, on the other hand, is a radical that it only exists for very short times at very high temperatures. So if you can image CH, we argue that it marks a chemical reaction layer. But there's an argument as to what chemical reaction layer are you talking about. Now, if you run Chemkin, you can compute CH, but not with a whole lot of confidence. CH is a very hard radical to to compute with any chemistry scheme. So you can see sort of where the chemistry occurs with CH. Formaldehyde is another radical that you can image, and I'll show you some. It's again due to the breakdown of the hydrocarbon fuel like methane into formaldehyde, CH2O, and it fluoresces very nicely, and it does mark where gases are hot on the reactant side of a flame. A technique developed at Sandia and at Cambridge that we're using is OH formaldehyde overlap. Now, if you can get an oxidizer and a fuel to occur in the same place and then image them, you know that a reaction's occurring there, assuming it's hot. And OH only exists where it's hot. And so at least we know the formaldehyde OH reaction occurs wherever we see both of them present. But that reaction zone may not be the same reaction zone as what you image with CH. So interpreting what you get from these diagnostics is still an issue. I won't say too much about Raman scattering, but we're undergoing an interaction with other labs that will help us to do Raman scattering. If you go into an academic career, I strongly urge you to do what my students do, and that is they go to a lab that has more lasers than we have, In fact, the last Air Force meeting I went to, everybody was joking, like, I need 12 cameras and I need 7 lasers, so how am I going to do that? Well, we have to collectively work together. And the Europeans are doing that, but for example, Sandia in Livermore and the Air Force in Dayton, Ohio, they are really doing a good job, if you ask them nicely, especially for young assistant professors, to put a lot of lasers together and do things like Raman, because it normally isn't done at universities. And we're also doing cars with them, but they're doing the cars. So to get us thinking about this, the Mie scattering gives you an image like the one we've got here, and you can visualize the oil drops with a green laser sheet. There is the issue that if the flame extinguishes, these little particles still disappear because they go into hot gases. And so when I draw an edge around that flame, I don't know if the flame is really burning at that edge or not. Most of that boundary, it probably is burning, but the droplet method will not tell you if it's extinguished. Also, if there's a more distributed reaction or a broad reaction, it'll only tell you where the leading edge of the reaction is, because once the droplets go, they evaporate, they're gone. So as you get into high Reynolds number, very turbulent flames, this oil drop method is not so good. Rayleigh scattering is based on the theory of Lord Rayleigh, and he explained why the sky is blue. Have you covered that in some of your classes, Rayleigh scattering? Well, the blue light from the sun is preferentially scattered down to your eye by the dust or large molecules in the atmosphere. And you can use that as a diagnostic. The Rayleigh signal that you measure when you scatter, when you shine a laser sheet through a flame, as I've shown here, you get light scattered by the molecules. Mostly nitrogen, because that's what's present about 70% of the time. And the fuel is present in some places. In this case, where it's green, you would have fuel and oxygen and nitrogen. And where it's blue, you would have nitrogen, CO2, and H2O, and possibly some O2 since it's lean. So now, how do you get any information from this signal? It depends on the number density, molecules per cubic centimeter, and the cross-section sigma, which is in square centimeters. And the sigma is pretty much proportional to the size of the molecule. So if you write this equation, it doesn't do you any good unless you can somehow argue that most of these cross-sections are about the same. Now, since the gases are mixed in a premixed flame, the fuel, the oxygen, and the nitrogen are all mixed on where it's green, what you want is that the total cross-section, the average cross-section of those three gases is about the same as the average cross-section in the products. And since most of it's nitrogen, that's a pretty good assumption. But you can even tailor the fuel composition to make it exact. So if you do that, then you get this equation at the bottom that says that if all the sigmas are the same and equal to sigma of N2, all the little n's add up to the total n, the number density of the mixture, and the number density of the mixture at any point is P over R is T, where R is, I should have put a subscript, that's the universal gas constant, not the gas constant for any particular gas. So it should be R sub U. And now, if the pressure is the same everywhere, which it is in an atmospheric type flame like this, then you see that the Rayleigh signal is inversely proportional to the temperature. And so that's how people measure temperature in clean flames. But you can't have any soot or particles or drops or anything. Now, there are a few ways to measure the chemical reaction zone. The two that are established are the overlap of formaldehyde and OH. There's an image of the overlap in one particular experiment in Sydney. A CH, this is a thesis of Bo Zhao, and I hope I'm pronouncing that right. I was on his thesis committee, so he insisted that I say it right, but he did a very nice thesis in Lund, in Sweden. And then the gas turbine people in DLR in Stuttgart, Germany, are looking at these flames, and again, they're imaging with fluorescence. Now, if you're not working with fluorescence, I'll just give you a brief overview. Some of you, I guess you can't be in the other session because it's right now, and so you can't do the laser diagnostic session. But this is only a couple of slides, so we say that fluorescence is the absorption of laser light followed by the spontaneous emission of light at a longer wavelength than the laser light. So if you look at the ground state of the OH molecule, that would be the lower line. Now you would excite OH molecules, which means you take the electron that's in the ground state and you raise it to a higher orbit. You can imagine the electron going to a larger radius. And it would go from the lower laser coupled state up to some excited state. But this is a upper state has to be allowed by quantum mechanics. So the states that I've drawn here, you can't choose. Those are set by quantum mechanics. So you have to pick a laser that has h nu, where nu is the frequency of the light, would be the energy per photon, and that energy per photon has to be exactly the right amount to take you from the lower state to the upper state. So with OH, that turns out to be 282 nanometers, which is in the ultraviolet. At CH, it's 390 nanometers. And you see that lots of other species fluoresce, different wavelengths. Unfortunately, a lot of species don't fluoresce. For example, we'd like to know where the hydrogen is, H2. You can't really get that to fluoresce. The O2, the water vapor, H2O, you might be able to do methane, CH4, but it's difficult. So this is kind of what we're left with, and oftentimes we'll put one of these species in with the fuel, like acetone in with the fuel, and then argue that the acetone stays with the fuel. And I've had students put NO2 in with the air and argue that the NO2 stays with the air, and so they're tracers that tell us where the gases are that don't fluoresce. But as you can see, the light coming out has to be at a longer wavelength because the energy of the photon coming out is less than the energy of the photon going in. And energy and wavelength are inversely related. Okay, so this is a formula that is really from Ron Hansen's classic paper. If you're doing laser diagnostics, you always have to worry about all of these quantities because you're trying to get the most signal out. And the more signal, the better your result will be, the more likely your thesis committee will be happy with your experimental results. Now, the steady state relation is that the rate of molecules excited by absorption has to equal the rate of molecules that are lost from the excited state by spontaneous emission. Now, Einstein said that after 10 to the minus 8 seconds, an electron will just spontaneously jump from whatever state it's in to some other state. And this is a real philosophical question. Why do they do that? And that's one of the unsolved questions of the universe. Why is it 10 to the minus 8 seconds? Why doesn't the electron just stay there? That's one of the fundamental rules of quantum mechanics and physics, and maybe you can figure that out. But it's kind of an interesting idea that electron will not stay there; it will move to another state. I guess it has to do with the uncertainty principle that it just wants to go somewhere else. But anyway, it goes to another state, and when it goes to another state, it will emit light. But if it doesn't go to another state, in other words, within this 10 to the minus 8 seconds, you could have another molecule come in and hit that excited molecule, and the two will collide, and the energy from that electron will go into the other forms of energy of the molecule, vibration, rotation, translation, and you won't emit light. So this is collisional quenching. So that's what this first equation says, that I nu is the intensity of the laser, NOH is the number density of OH, F is a Boltzmann fraction because not all of the OH are in the lower laser coupled state. So, most of them are, but not all of them are. B12 is the absorption coefficient. Now, NOH star is the number density of excited OH molecules. A21 is this famous Einstein emission constant. And then the collision rate between the OH excited molecules and anything else is given by NOH star times Q, where Q includes the number density of anything else that collides, including mostly nitrogen. So if you take that first equation now, you solve for NOH, you simply see that A and Q add together, and then you stick the value of NOH from the first equation into the second equation, you get the signal coming out, and that's this lower equation. Okay, so if you just want to see where the OH is, and you don't want to do quantitative work, you don't need to know what these values are. You just look at the signal and say, well, there's OH there. But other grad students that have worked with me have said, well, I want to know the exact number density in molecules per cubic centimeter. Then you have to determine all of these quantities, it's difficult. Okay, if you want to optimize the signal, which you may have to do, you would write that equation in a slightly different way. You would take intensity, which I think I didn't write it, but it's proportional to the energy per pulse divided by h, the height of the laser sheet. And So energy per pulse and height of the laser sheet, H, appear. The total number density multiplied by the OH mole fraction gives you the number density of OH. And so if you put that in, you have a P over T factor. And the Fn is the F number of the lens. And the smaller that is, the better the lens is, the more light you get. So if you're running an experiment, one thing you can do is bin the pixels. In other words, if you have 1,000 pixels by 1,000 pixels, you do a spatial average, and every 4 by 4 pixel region, you spatially average that and assign that number to all 4 of those pixels. Now, you get better signal because it's as if you have one big super pixel that's 4 by 4. But you lose spatial resolution, you might lose some information, but you get more signal to noise. If you reduce the height, H, you'll get more signal because the laser energy will be spread out over a smaller volume. Smaller F number lens is good. And of course, if you could increase the gas pressure, that would be good too. So limitations are that you have to have an available laser that will excite at the frequency you're interested in. And now as we start to do kilohertz diagnostics, it becomes even more constraining because a lot of the kilohertz lasers won't operate at all the frequencies you want. The molecule must emit in the visible, where we have cameras. One of the grad students, David Rosenberg, was working with me, and I remember we were down the lab together, and we just couldn't get any signal out. It wasn't working at all, and then we realized that the camera that we had, which was about a $50,000 camera, wasn't quite as sensitive as we would like in the red, and so he said, well, will you buy me another camera? And so I said, well, I don't know. I'm not going to be able to go to Acapulco, Mexico this year if I buy another camera, you know. But no, I bought him a camera, and he was able to do his thesis. But without the right camera and without the right laser, you just can't do it. So that's why people are teaming together as much as they can to help each other out. The fluorescence wavelength, the light that comes out, must be separated from fluorescence from other species. Now, we put laser sheets into, let's say, spray combustion, where there's a hydrocarbon spray like Jet A fuel, and there's just a million species there. The hydrocarbon fuel breaks down into many, many things. And so when you shine the laser in and you see some light coming out, you think you're tuned to a particular molecule, but you may be tuned to many molecules. If you want to get quantitative information, it takes, it'll add another year or two to your PhD thesis, at least. You must have large windows, which is a problem if you're operating at high pressure. Background noise can come from lots of sources, and if you shine UV light through glass, it will get very bright because the glass will fluoresce itself. Anyway, if you're interested and you're not working in this area, I recommend you look at these books. If you're working in this area, I'm sure you're familiar with these books. Okay, I'll tell you a little bit about now what my students have been doing on an Air Force project. We're doing OH formaldehyde and CH-PLIF. As I speak, they're back taking data, and they have lasers in our lab that are set up in this particular arrangement so that we get 532 nanometer green light. We get 283 by doubling it to excite the OH, and we're using 355 directly out of the YAG laser to excite the formaldehyde. And we also have a beam in here that's at 390 that excites the CH. Okay, so what does all this tell us? Well, I asked the students to run ChemKin for a premixed flame, because we're studying a premixed flame. And here are the profiles you get when you run ChemKin. You see heat release is the dotted line on the right. And formaldehyde is the curve, it's labeled on the top left. And it's very broad. And the temperature goes up across the premixed laminar flame. Now, the formaldehyde is not reacting everywhere where it is. The formaldehyde is formed in the reaction layer, and then it diffuses away from the reaction layer, in this case, upstream. Just because you see a species doesn't mean it's reacting at that point. It can diffuse away. But where I put CH2O times OH, now that curve is a narrow curve that overlaps the heat release. And so if you could image the two together, you'd have a good idea where the heat release region is. And we argue that the formaldehyde, since it diffuses upstream, it's visible everywhere until you get to be, about 400 Kelvin. If you image that region where there's formaldehyde upstream of what we call the reaction zone, or the heat release zone, if it's just formaldehyde and no OH, then we'd argue that's the preheat zone. So that's what we're doing on this. The formaldehyde marks the preheat, and the overlap of formaldehyde to OH marks a reaction zone. And we tried this on a premixed Bunsen flame that's laminar. And you see you get these two images, and right where the two signals overlap, we argue that is the reaction zone. And it does have a width approximately equal to what's predicted by ChemKin. Okay, so the reason we're using these diagnostics is to study premixed turbulent flames at high Reynolds numbers and high turbulence intensities. So this is the classic Borgy diagram. The turbulence level is plotted on the left. The integral scale, normalized by the flame thickness, is on the x-axis. And Borgy and Foreman Williams and others have argued that, and Norbert Peters have argued that these are the regimes. But they had no experimental evidence. They were sitting at a desk with a number 2 pencil, probably, and telling us what's happening. And so the question is, are they right or not? And they did have some experimental evidence, but not much. Assuming they read the experimental papers, I think they did. Anyway, this bottom line is the Klimov-Williams line, where the Kolmogorov scale equals the preheat layer thickness of a laminar flame. And so Klimov and Williams argued that once the smallest eddies get inside the preheat zone, they're going to start to broaden the flame, and it's going to go from corrugated thin flamelets, which means basically thin flamelets that are just wrinkled laminar flames on the bottom of this orange line, to broadened preheat thin reaction zones. And that's what Norbert Peters argued is this regime between the two orange lines. But then he also said that once the Kolmogorov scale gets inside the reaction zone, you go above into this green region, and that would be broken reactions. No one has ever confirmed that. And then if you go way up to the right, that would be large Reynolds number, In other words, large integral scale and large turbulence level. If it was sufficiently large, you would say, well, maybe that's distributed reactions. But again, nobody's measured that or confirmed that. And so now we've done about 27 cases, and all of them are within this rectangular region that I've shown here, and some actually go below. I show a few squares there, but we've done 27 cases and looked at the flame structure. Okay, so this is what I said. Peters predicts broken layers when the Kolmogorov scale gets inside the reaction zone. But there's a lot of controversy about that. First of all, the Kolmogorov scale is so small, it's so weak that that eddy can't even turn over once, and it just dies just because of viscosity. So there's nothing very impressive about a Kolmogorov eddy. And a flame, on the other hand, is a pretty strong animal because the gas, premixed flame, the gas goes into it, and then it accelerated to be 6 times the velocity normal to the flame. So if you got 20 centimeters per second coming in, you'll get 120 centimeters a second going out. So that's a huge acceleration, and it's not really clear that a little eddy can do anything to that. So we sort of question for many years people have questioned, could Peters be right? Is any of this right? Also, the viscosity of the gas changes. So the Kolmogorov scale down here and the Kolmogorov scale of eddies going into the flame could be quite different, because as gas heats up, it becomes very viscous. But we need to know these boundaries and more information, because if you have a flamelet model, and many people do, a lot of people say, oh, that model will never work for a jet engine or a rocket or anything realistic. But maybe it will. Maybe we can modify flamelet models to be practical. But if it's a totally distributed reaction, like just a big glob of chemical reaction, then probably a flamelet model would not work. So there's a question, can we get models to work where we have broadened flamelets, which would be, you can imagine wrinkled thick flames, but they're a lot thicker than a laminar flame. Maybe you can. But probably not for distributed, so we need to know the limits. So what my students did on this project is here's a very turbulent flame that this is a Bunsen flame, and they imaged formaldehyde and they imaged OH. And you can see that the image on the left sort of fits inside the image on the right. And so if you're very careful and you align everything up just right, and you calibrate in the laminar flame, and you get these images that are on the bottom, which would be the overlap. Again, it was developed at Sandia and at Cambridge. And then the students use MATLAB to define a skeleton, which means a red line that goes sort of in between the layers and properly goes into broadened zones as well. And then they can measure the perimeter of that skeleton. They can measure the distance from that skeleton to the 2 nearest edges normal to the skeleton, so they can get some thicknesses of these weird shaped things. And so we argue that some of these globs look sort of distributed, whereas other places we see broadened flamelets. Now another method, and this is a study that a student from Russia did with me a long time ago, and that is we looked at CH PLIF, and we got these black images. This was done about more than 15 years ago, so people can do better than this. On the other hand, we did both simultaneous PLIF and CH and PIV, so we could image the vortices, and these, you see all the little eddies and where they were going into this flame. But these are not kilohertz, and so we can only get them at random times. We couldn't get movies like we can today. Anyway, then, once you image where the reaction zone is, where the OH is, you can get experimental results like the picture on the left. And the people at Lawrence Berkeley Lab spent a lot of computer time and computed this with DNS. And it's an interesting exercise. I think many of you will have to go through this, and that is you're trying to compare experiments and computations, and usually they don't agree at all when you first start out, and then you realize it's not that one of them is bad, it's probably both of them are bad. That's what we found, okay? This student, Sergey, he swore by his measurements, but then I said, how carefully did you measure the boundary conditions? And he said, oh, I know those. I said, go back and measure them again. And sure enough, not the boundary conditions of coming into the flame, but the outside of the flame we had two pilot flames that were providing hot gases on the outside. And sure enough, when we measured that more carefully, we found that the original numbers we were giving on the pilot flame were not right, and that's why we weren't getting any kind of agreement with the DNS. And so we got that right. And they did some iterations too. They made sure they were resolving the scales. And anyway, they got about the right height to the Bunsen flame when all was said and done, and we were happy. But it took them a lot of time, and it took us a lot of time to get this comparison done. And now we're running a circular Bunsen burner, which is 26 millimeter in diameter, with a pilot flame around the outside. And we can run this up to a turbulent Reynolds number of 100,000, which means we have a mean velocity of 78 meters per second. So this is about 16 times more turbulent than any other Bunsen flame that has been studied using laser diagnostics. And we've been putting JP8 into it, as I show you. So there's a big co-flow. It's really loud and noisy and somewhat dangerous, so you have to be in another room. But you can get the turbulence to be uniform across that pipe in the middle. And some of the conditions are that we can get very high turbulence levels of divided by U prime divided by the laminar burning velocity of up to 243. And as I say, that's about 16 times what other people have done. And it takes a lot of airflow and a lot of fuel. It's a pretty big device, okay? But then that allows us to get some data points up in this broken reaction zone above where Peter says we should have continuous flamelets. And I'll just tell you right now that even though we've got, we have 27 cases total, and I would say maybe about 10 of those are above Peter's boundary, and we see no broken reactions. Yeah, so we disagree with Norbert's predictions on that. But this is a typical flame where, again, the red is the OH, the blue is the formaldehyde, which tells you where you have a preheat zone, and the overlap is between the two white lines. And so the students working with me have taken thousands of these types of images and have analyzed them. And if you just look at the preheat zone, this is the formaldehyde. This is the picture you get. As you go up in turbulence level, it becomes very strange. The one on the left is what many, many people have recorded before with Rayleigh scattering and other things. But as you go to a very high turbulence level, we're seeing a very, very brushy looking preheat zone. And on the other hand, we look at the reaction layers where the overlap method is applied. And I guess to our great surprise, we thought they'd get broad, but they don't get broad. They sometimes get a little globby looking. But if you take the average thickness of these pictures, it's only about twice as broad as a laminar reaction zone, a laminar flame reaction zone. So we can say that based on, to the best of our measurement abilities, the reaction zone is not broadening. Even, and this is for all 27 cases. Furthermore, we said, well, where are they breaking? Well, you know, I've got a few arrows here where maybe it's breaking, but if we look at statistically the data, it's not very large. It's a few percent of all the images where we see broken reaction zones. So we are saying that to the best of our ability that it looks like Norbert Peters is wrong about his about one of his predictions. Now we are seeing that the preheat zone gets thicker and thicker, and the reaction zone stays about the same, which up to a certain point is what Norbert said should happen. But then why is this? Well, I don't think he ever said why. He said that the eddies are not going into the reaction zone, but there's some work by Guillaume Blancard at Caltech in computations, and some work by Andy Aspin at computations in England. And they are looking at the vorticity and the eddies as they go through flames. And we haven't yet been able to do this experimentally, but we're working on it. But you asked the question, you know, if you have turbulence, does it ever get to the reaction zone? I mean, if you have a really thick preheat zone, like I showed you in those fuzzy pictures, what happens is you've got like a centimeter or maybe even 1.5 centimeters of preheat zone, and you know, will an eddy go through there? So maybe we need to change our theory of turbulent combustion a little bit. Try to look at the structure of what happens. Once they do get through this thickened preheat zone, they are definitely attenuated by viscosity, and maybe they're too weak to do anything. Maybe even the integral scales don't even make it. And this would sort of imply that this reaction zone is pretty much living a laminar life, you know, and doesn't really even know there's turbulence. I don't know. But now some work done in France by Poinceau in Toulouse, and actually when he worked with Sebastian Candel, so Sebastian actually supervised this work, is, you know, what's the efficiency of what happens to eddies? Do they get stronger? Do they get weaker? What happens to the eddies? And what's the relative role of the eddies in doing things like broadening or wrinkling flames? And so they did numerical simulations and computed a stretch efficiency function, which basically said, you know, eddies of different size stretch the flame in different ways. But we haven't yet measured these as well as we would have liked. And then there's another issue, which I'll leave you right before we take a break, and that is, how do you get distributed reactions? You know, we've talked about this. Now, obviously, if you take a big stick and you mix everything up really fast, like in a recirculation zone, you might have distributed reactions. Or if you have a piston in an HCCI engine, definitely you're going to get distributed reactions. But in a turbulent flame like I've described, where you have hot products on one side, cold reactants on the other side, if the flame is continuous, the gases are going to accelerate really fast towards the hot products. And so it's going to be really hard to mix those hot products back into the cold reactants, right? Because they're trying to go this way at a really high speed. So you'd have to have a pretty strong eddy to do this. But if you broke the flame, then you wouldn't have to fight against this acceleration caused by the flame, at least in that little region. So maybe you could mix. So maybe Norbert, what Norbert meant to say that was that first you have to break the flame and then you can get distributed. And so maybe there's several steps in the process. Anyway, we're able to begin to image these types of things and maybe answer some of these questions. We don't see this yet. I mean, is that what you're asking? No, there's no proof. There's no proof. I'll show you some evidence in the next few slides after the break, but there's a little bit of evidence in a Bunsen flame. What we really need is for lots of people to study lots of different flames, get all their lasers together or computations together, and yeah. Yeah. Well, yeah. If you, okay. So, if you do the overlap method or the CH method, you look for holes in the reaction zone, and then you would like to do simultaneous velocity to see if there's an eddy right there. So, simultaneous OH, CH, formaldehyde, and PIV at very high Reynolds numbers, very high turbulence levels. If you can do that, you're okay. Now, some of you may be able to do that. But let's take about a 15-minute break. It's 1:15. Maybe we'll start again at 3:30.